Ladies and gentlemen, please join me in welcoming this year's Van Horn lecturer from the Department of Material Science and Engineering at UC Berkeley, Professor Geert Sieder. Before we get to Professor Sieder's presentation, let me quickly give you the background of this Van Horn lecture series, and then Professor de Geer will introduce Professor Sieder to you. So the Van Horn lecture series is in place since 1974, and it honors Kent Van Horn, who was a physical metallurgist. The name Van Horn is very omnipresent on this campus, and Kent specifically graduated here in 1926, I believe, and then moved on for doctoral studies to Heidelberg, Germany. And after his return and after his PhD, he worked with Alcoa, then moved to a small town called New Kensington near Pittsburgh, and eventually became the corporate vice president of Alcoa. And his father is Frank Van Horn, who is the founding father of what we now call our Department of Material Science and Engineering. He was a geologist and mineralogist, collected rocks, traveled a lot, and he was also very dedicated to sports. You may all know the Van Horn field in front of the Wield Center. I've read that Frank Van Horn actually established the first successful football team at this university. And there's also a son of Kent Van Horn. That's Carl Van Horn, who keeps in touch with our department. He started out as an engineer, but then became more interested in the financial business. And nevertheless, he has a close relationship, and we see him on the regular. So that's the background of this endowment that sponsors our Van Horn lectureship. And the department faculty every and each year screens the field of material science for an eminent scholar. In this year, Professor Sieder, who comes here and gives us 3 lectures. And the main target of these lectures are our students. And there are also a greater number of meetings with research groups and specifically graduate students, where we want to establish an interaction between the Van Horn lecturer and the students to share their work and to get some expert opinion on what we are doing here. So that's what I wanted to say, and now I hand over to Professor de Geer to introduce Professor Sieder.
Thank you, Frank, and welcome all who've come to hear the first of these lectures in the Van Horn series. It's a privilege and a pleasure to introduce them. A bit of background about Gerbrand Sieder. He received his engineering degree from the University of Leuven in Belgium in 1988. And from there he went to the University of California at Berkeley to get his PhD in 1991. Between leaving Berkeley with his PhD in 91 to returning to Berkeley in 2015, he was on the faculty at the Massachusetts Institute of Technology in their Department of Materials Science and Engineering. He is now the Chancellor's Professor in Materials Science and Engineering at University of California, Berkeley. He has over 450 publications with him and his group, an H-index of 122, and which are phenomenal numbers. But I want to give a bit of background about the subject area of materials for energy storage, the subject of today's talk. Professor Sater and some of his colleagues at MIT started working in this area in the mid-1990s. And they began with the goal of finding new cathode materials for lithium-ion batteries. And Professor Sater's contribution to the effort was the first principles, or ab initio calculations, in the search of new materials. At the time, this was a bold move. They knew that they were going to be looking mainly in the area of oxides, and first principles calculations in oxides were more complex and less well advanced at the time than for other categories of materials. The properties that they needed to explore and model relevant to cathode materials were multifaceted. They had to look not just at phase stability, but also at crystallography, at electron transport, and at ion transport, and optimize all these properties from a first principles calculations basis. That whole idea, the whole concept met with some skepticism back in the mid-1990s. But after several years, a new category of fast charging cathode materials, the lithium iron phosphates, had been proposed, proven, synthesized, and put into commercial production within about 10 years. And in 2009, a publication from Professor Sater's group on the fast charging capabilities of lithium iron phosphate materials was published in Nature, and that single paper alone has received over 2,800 citations in just 10 years. Now, Professor Sater, since 2015, has been recognized with 7 major international awards for his work. He has also, while he was at MIT, won 3 graduate teaching awards for his work on teaching of graduate level thermodynamics. But he's not just a scientist and he's not just a teacher. I also wanted to call attention to the fact that he is a part of the Safety Advisory Board for the Samsung Corporation to develop novel safety protocols for future lithium-ion batteries. His webcast course on computational material science is freely available at the MIT OpenCourseware network, and he reports that it receives over 15,000 distinct hits every 3 months. So it's apparently something that's worth watching and very well appreciated. He's a member of the American Physical Society's He was a member of the American Physical Society's study on critical elements for energy technologies. So he also recognizes the responsibility of scientists and leaders in their field to help shape not just new science and technology, but also energy policy and future directions. So it's time for us to let our Van Horn speaker for 2019 to begin telling his own story. Please join me in welcoming Professor Gerhardt.
Thank you for that very nice introduction, and I think that's the nicest introduction I've ever gotten. And thank you for having me here. I know it's only been 1 day so far, but it's really been wonderful. I think this idea of getting a sort of deeper introduction to some people's research is really so far a good experience. So as I was mentioning in the introduction, about 4 years ago I moved back from MIT, where I spent 24 years, back to my California, where I'm half-time at UC Berkeley and half-time at Lawrence Berkeley Lab. And if you ever consider contemplating a postdoc, this is the view from our laboratory. Especially if you stay late, you get that kind of view. So I've been working mainly in energy storage with the US Department of Energy, but also with 2 longtime sponsors of mine, Umicore, which is a company you probably don't know because they don't put their name on anything, but is the largest cathode producer in the world now. Produces a lot of other things, like in the noble metals categories for sure. And then of course for about 7-8 years I've also worked with Samsung. Though I like to point out that this note about me being on the Safety Advisory Board was after they had the incident with the phone. I like to stress that. Okay, so I'm going to stand here maybe so I can see my screen better. I just want to briefly introduce who we are. We're a group of about 35 people these days. That's really not just a students postdoc and some visitors. My passion has always been computationally driven design of novel compounds. Since I was a graduate student, I wanted to do that. But while in the beginning we were a pure theory group, since about the last 15 years really or more, we really are a mixed modeling experimental group. And that was really set up because I felt the interaction between experiments and theory had to be much more facile, much more rapid. And my experimental colleagues got tired of me asking them to do stuff for them. So we decided to set it up ourselves. And while our theory program spans quite a broad area of things, our experimental program is mainly in energy storage, and it's sort of funded by industry and government together. So what I'm going to talk to you about over these 3 days is today is electron energy storage, which I'll start out very generic, but then go a bit into the science of the materials and how you can make better materials truly through understanding the fundamental science. Tomorrow, again, I'll start with a broad take on how we got to the materials genome idea and high throughput computing, but then lead into what I think is the next challenge for computational materials design, which is sort of how do we make materials, how do we synthesize materials, and that'll be a bit more in-depth science. And then the lighter lecture will be the last one, which is our sort of introductory efforts to do machine learning and natural language processing, in particular to figure out to what extent machines can learn from the literature by reading papers, if I may sort of simplify the statement. So that's where we'll hopefully get through. So let me go towards energy storage. If you every few years, the BP makes an energy outlook report where they sort of look forward about 20 years. And basically the main conclusion from the last report, which just came out last year, is that the world's going electric, right? They predict that by 2040, all of primary energy growth. So primary energy means the basic energy, including petroleum, natural gas, coal, everything you put into the system before conversion will be for electricity generation. So that's clearly the main driver for energy growth. They predict that 40% of that growth will be satisfied with renewables. They also make a prediction that by 2014, 30% of all miles driven worldwide will be electric. That does not mean that 30% of all cars will be electric. It means 30% of all miles driven will be electric. And that is heavily relying on the ride-sharing economy, that part of that will go electric, and that autonomous driving will go in part electric. Sorry. So if you look at sort of needs for energy storage, right, they are everywhere. And in many cases, if you can store energy, it's often led to a better experience. The fact that we can store electricity has essentially created laptops and smartphones. But there's even other things that I think if you're not a tinkerer like me, you may not experience. We now have cordless power tools that are actually better than the ones you plug in, because even these small battery packs can generate more power and torque than something you plug in your outlet. Actually, there's a funny story when DeWalt was first introducing lithium-ion battery packs for drills. They actually found that customers would torque their screws, over-torque them all the time, and basically break them. Because as you know, electrical drive can generate an enormous amount of torque. And so by now, there is no serious contractor anymore that uses corded tools, because they are simply a better experience. The same is true with driving. If you've ever driven an electric car and you sort of get enormous acceleration, I'm not sure you really want to go back. While there's still range anxiety, the drive is just a much better experience. And even these fields where we never thought lithium-ion technology would go, like grid and aircraft. Aircraft's the one that really surprised me, that you never think aircrafts would go electric. But there is enormous effort in making short-range aircraft electric. And that is driven in part by fuel efficiency, but it is also driven by ancillary issues like, electric aircraft is quiet, so you may get landing rights at times where normal aircraft cannot land. So in congested airports in, London City, Paris, Brussels, where, you know, in London you're not allowed to land before 6 a.m. In Brussels you're not allowed to land overnight because it disturbs the community. People want to go in with electric aircraft, right? It's a lot quieter. Some of them will have vertical takeoff and landing, so you can go into very small airports. You actually don't need a landing strip. So that is largely what is driving this. And if you don't think this is real, I urge you to look this up. This is much farther ahead than any of us think. There are test flights already that are simply battery powered, which is actually quite remarkable. And then, of course, the grid, I'll say a little more about. You know, in grid, energy storage is an enormous need, right? This is actually both real data and a projection of California's needed electricity generation that's not solar. And what you see is that basically as more solar comes online, which is basically between these hours here of sort of 9 to 5 p.m., the more solar you get online, the less electricity you need to produce. And that generates what's now called, what was coined at NREL by somebody as the duck curve, right? Because you can sort of see a duck in here. But you have to look at the scale here, right? This is in thousands of megawatts, so gigawatts. So between about here, sort of 4 p.m. and you know, 8 p.m., you have to ramp up about 14, 15 gigawatt. I don't know if you know the scale of electricity, but a large power plant, like a large nuclear power plant, is sort of order of magnitude of a gigawatt, right? So you're essentially talking about the equivalent of turning on 15 nuclear power plants, which of course you cannot do, right? So there's an enormous ramp here that you have to deal with as more solar comes online. California is probably one of the worst states if you look at like the sort of northern central region of the United States, where you integrate this with wind. This curve looks slightly better because the complementarity of wind and solar. So if you think back 15, 20 years ago and you think about how you're going to store energy, there's in principle many ways to do it, right? You know, people do it in capacitors for a while. People even want to do large-scale energy storage in capacitors. There's lots of mechanical ideas out there, pumping water being one of them, compressed air, flywheels. For a long time, people were investing in flywheels because since the energy stored goes like the velocity squared, basically if you can spin something really fast, we're talking 100,000 RPM here, you can in principle store a lot of energy. That field is largely dead because it sort of became an engineering problem, right? If you spin things at 100,000 RPM, engineering the bearings is really hard, and the safety issue is major too, right? If something breaks at 100,000 RPM, it's essentially a deadly projectile. And then electrochemical is the one I'll talk about, but they're actually more exotic, right? There is still some use of superconductors in the grid. One of the interesting things about superconductors is, as you know from physics class, right, you can make a superconducting energy storage ring that essentially runs forever, in principle, as long as you cool it. And the nice thing about it is you can couple into that with any control of phase angle you want. So you can have like capacitive response, you can have other response. So you can actually store, you can actually control the phase angle between current and voltage and stabilize the grid with microsecond response. And so DVARs, as they're called, are sometimes still used for that, but this is of course not a big scale energy storage device. So out of all these, right, the question is what technology is being used? And this is sort of an interesting lesson why there's a lot of things that make sense in principle. Well, obviously, as you know, in portables, power tools, and automotive, it's all lithium-ion, right? There's nothing else competing anymore. In the grid, as I'll show you, it's actually largely lithium-ion today as well, something that nobody would have predicted 15 years ago. And in aircraft, we don't really know yet. Testing is all done with lithium-ion. But there's some people who say lithium-ion will not get there, will not get to the right sort of energy per unit weight, but we'll see. So there's sort of a question, why is that? And I'll come to that a bit, right? But I want to first give you a few facts, right? For all the talk we had about alternative methods of storing energy, in the last year, 95% of all storage that was built into the grid worldwide that was not hydro was lithium-ion. So while we have a lot of other ways in principle to do flow batteries, to do mechanical things, it's all lithium-ion. And why was that? Because lithium-ion is something you can buy today. It's reliable, it's cost-effective, and that's why the utilities buy it. One of the more spectacular ones until recently was the one Tesla built in South Australia. Australia has a terrible grid situation. They have enormously variable peak pricing. Some of the pricing is very high on occasion. So they wanted backup, and Elon Musk with his brazen self essentially said, I forgot what he said, he was going to build it in 6 months or a year, and he actually did. It's a 129 megawatt hour plant. It cost about 69 million, but in its first year it made 25 million in operation, and simply by arbitrage. Now you can do that in Australia, where spot pricing of electricity sometimes truly shoots up. But this is one of these things when you're the first mover in a field where you actually made a lot of money for the operating concern that did this. But even bigger is coming, right? If you look at what PG&E is Pacific Gas and Electricity, is my utility, has a few months ago approved about 3.3 gigawatt hour to replace gas power plants. And here's the four, they're all going in the same place, South Bay Landing, which is somewhere down south of Monterey and Carmel in California. And if you look at the technology going in, all the same. And I want to show you something interesting about that too, right? So this was approved a few months ago. This is the projected online date. So because you're building something that's actually not that hard to build, essentially a lot of these are going to go online within 18 to 24 months, right? So siting permits, installation is all much faster than putting, say, another coal plant or another gas-fired power plant on there. And this is starting to count, right? This is 3 gigawatt hours. This is a serious amount of energy storage backup. So that has propelled lithium-ion into a remarkable market, right? And in part you can see why this is market segmentation for lithium-ion in about, I think this is the 2017 numbers. If you look at only 25% of lithium-ion went to electronics anymore. This is your smartphone, your laptops. Already more than 50% went to automotive. Now I want to put that in perspective. That's 50% of all lithium-ion, but that represented only about 1.5% of the automotive market, right? So less than 2% of the automotive market is electrified, meaning EV or plug-in HEV, so anything that has a plug that can take on external power. So you can see the potential growth, right? Even with 1%, you're already taking up 50% of the lithium-ion market. And the growth numbers here, right, in 2000, we barely produced 2 gigawatt hour of lithium-ion, which is about 200 million smartphones, basically. In 2017, this number is probably a little underestimated. It's somewhere between 120 and 150 gigawatt hour. We made projections in a paper 2 years ago that by 2025, 500 gigawatt hour would come online. The reviewers of the paper said we were crazy. And now we're actually being criticized for that number being too low already. And people are projecting about 1 terawatt hour of production, right, by 2028. And this is mainly a cost issue, right? That, you know, lithium-ion, if you extrapolate this, I started in the field well before this when lithium-ion was well over $1,000 per kilowatt hour. Today, at the pack level, so this is fully packaged with electronics, it's below $200 already. And at the cell level, if you just want to buy cells from in large volume, it's hitting about $100 a kilowatt hour. And that's coming down from over $1,000 a kilowatt hour. So, you know, a message that I'll have for you later is also never underestimate the incumbent technology, right? It moves, it gets cost out. And so when you build a new technology, always think about your target is not what that technology is today. Your target is what that technology will be 5 to 10 years out. And so for lithium-ion, that's been a tremendous cost curve, right? So that was sort of my broad setting. What I kind of want to lead you into a bit, what are the scientific challenges on the material side, how you fix them, and then where I think energy storage will go next. So let me give you like a very short primer on lithium-ion. It's essentially a shuttle device for lithium ions. You know, you have an anode where lithium sits at high chemical potential. That's typically lithium in graphite today. And then you have a cathode where lithium sits at very low chemical potential. So if you remember your thermodynamics, the Nernst equation tells you that you can build up a voltage. That's the difference in chemical potentials. And for lithium-ion, that difference is remarkable. It's close to 4.5 volt, which, again, remember, water splitting is about 1.2 volt. The way you store lithium is by intercalation into an oxide. So typically there are these layered oxides. This is a picture of lithium cobalt oxide. where you have, it's this layered structure. You have cobalt ions, lithium ions, cobalt ions, lithium ions, and you basically shuttle lithium ions back and forth in and out of the structure. So you store lithium kind of like in a material, like a sponge, right? In discharge, the lithium sits at the cathode. In charge, you pump it back up electrochemically to the anode, and then in discharge, you release it again. So what are some of the challenges for the industry? And now I'll go into why you have these scientific challenges. One is that we are a major taker of cobalt and soon of nickel. Today, 55% of all cobalt produced in the world is going straight into the lithium-ion industry. This is a major issue because I'll talk a little bit about the sort of way cobalt is produced. And then the other one is safety, right? Even though the safety record of lithium-ion is in general very good, incidents are costly. They are well publicized. You know, the Samsung Note 7 incident, which I'll be happy in question time to tell you a lot more about why and how it happened. It's an interesting engineering story. But that cost the company $7 billion, right? Because every Samsung Note phone was recalled, right? You know, Tesla fires. I used to have a picture of the Boeing 787 grounding, which cost the company was probably the biggest loss in its history, except for now maybe what's going on with the 737 MAX, right? So cobalt issues, we produce about 110 kiloton today. Cobalt is a byproduct. There are very few pure cobalt mines. Cobalt is a byproduct of copper and nickel mining, mainly copper mining, which means that you can't just go and mine more. Almost nobody will go and mine more copper so you can get more cobalt, because the value of the copper is still the main thing you mine for. So there's only sort of so much you'll get out of the ground in a given year. Our projection is that you'll need somewhere between 140 and 300 kiloton by 2025. The other issue in terms of resources is that when you think of criticality of resources, you think a lot about geography. And what this shows is which fraction is located in a single country. And for cobalt, it's one of the worst elements ever. More than 50% comes out of the Democratic Republic of Congo. And democratic is a misnomer here, right? If you know how the regime in Congo worked. You know, as I always say, Congo is only like one dictator away from even more chaos. But that's actually where 50% of our cobalt comes from. About 25% of it is from artisanal mining, which is basically people digging up dirt with their hands, right? The other 75% is more commercial mining efforts. Okay, so the question is, why do we need cobalt? And I'm going to broaden that a little bit. If you look at cathode chemistry today, we basically only use 3 elements. So if you look at what's in your phone, it's pure lithium cobalt oxide still, right? It's the densest material, and if you're Apple, you care about shaving 1/10 of a millimeter of the thickness of your laptop, which is crazy, but that's why they go for super high energy density, because I want to say if you cut open your Apple laptop, which you shouldn't do, get a YouTube video, right? You can actually, somebody's done this. Your laptop is not a laptop, it's a battery carrier, right? The 2/3 of the space inside your laptop is taken up by battery. It's really not in many different pockets. It's not a single battery anymore. So it's all about energy by volume, and lithium cobalt oxide is the pure winner there. But if you look at automotive technology, it uses substitution of cobalt, things with nickel and manganese, but it's essentially the same layered compounds that I showed you in the beginning. And they go by exotic names like NMC111, NMC622. That just stands for nickel, manganese, cobalt, and the ratio of elements is these numbers. So NMC622 means 60% nickel, 20% cobalt, 20% manganese. This is the staple of the EV industry today. If you buy a Chevy Volt, it has 622 in it. I would say besides Tesla, most of the market uses NMC622. If you have plug-in EVs like mine, that's more like NMC111, so it has a much higher cobalt content. If you're Tesla, you use something called NCA, which has aluminum instead of manganese, but it's still the same set of layered compounds. So the fundamental question that we asked ourselves is, why after 30 years of cathode research are we limited to 3 elements? And that's an interesting story. It turns out it's a very fundamental piece of physics. If you take a layered cathode, and I made a cartoon here, so when you charge the battery, you extract lithium, right? And what happens in many materials is that you got an enormous amount of vacancies. We pull out as much as 75% of the lithium. So you create all these vacancies, and what's going to happen in many cases, these transition metals just will migrate in there because they have to make a single atomic hop to actually just get in there. And why is that bad? Because what happens is that because the transition metal has higher charge than lithium, it's 3+ or 4+, it pulls the oxygen layers closer. So it essentially densifies the structure. And what that does is actually increases the activation energy for lithium motion. And the reason is quite simple. This is essentially an ordered rock salt. So it's an FCC packing of oxygen. The cations sit in octahedral sites. And to migrate from one octahedral site to another octahedral site, they have to go through a tetrahedral site. That's just the crystallography of the FCC. If you ever stare at it carefully, on every face of an octahedron is a tetrahedron. And this is the activated state. When lithium is in the activated state, it's very close to the transition metal. So this electrostatic repulsion controls the activation energy for lithium diffusion. So now you can see if the spacing here is large, then these ions can stay away far from each other, and you have good lithium mobility. If you condense the structure by making these planes come together, you actually increase the activation energy for lithium, and you have no motion anymore. So you cannot charge and discharge your battery at a reasonable rate. You can back that up with ab initio calculations, where we actually can artificially control the slab, and what you see is the activation energy goes up dramatically as you contract this slab. And as engineers, you should learn to appreciate the numbers. You know, if you put something in an Arrhenius factor at room temperature, every 56 milli-electron volt causes an order of magnitude of the Arrhenius factor. And here, to get a 56 milli-electron volt, the slab has to change by only 0.1 angstrom. So you only get a change in sort of lattice parameter by 0.1 angstrom, and you lose an order of magnitude on mobility. Okay. So let's get to the science. So why is only cobalt, nickel, and manganese good? Well, that has to do with the mobility of these ions. It turns out that some have a much easier time to migrate from one octahedral site to another. And remember, I told you they have to go through the tetrahedral site. So what it turns out, the activation energy for metal motion, not the lithium, for the transition metal motion, depends on its electronic structure, because it depends essentially on how ambivalent the biz is about its coordination, right? It sits octahedral. If it doesn't mind being tetrahedral, then it's going to easily migrate through this because it has to go through a tetrahedral site. Well, that depends on the electronic structure. Because if, you know, a transition metal has 5 d orbitals in an octahedral environment, they split 3 down, 2 up, just because of crystal symmetry, right? These are called the T2g orbitals. These are the EG orbitals. And this is essentially the gap created by the octahedral coordination. So in sort of basic, simple principles, what you want to do is you want to fill these electron states, because then you will fully prefer octahedral coordination and not fill anything else. So let's go through the periodic table now, right? So basically we have 3+ or 4+ ions, right? 3+ in the discharge state, 4+ in the charge state. So I'll put on the 4+, the 3+, and in some cases the 2+ are relevant as well. So like you take titanium 3+, right? This is not going to be a good ion because it has only 1 electron in its stabilizing energy level. So titanium will migrate, and that's exactly what it does. So does vanadium and chromium. Because chromium looks great, because spin polarized, it has 3 electrons, but when you oxidize it, there's only 2 left, and you don't have enough stabilization to keep it in the octahedral site. So basically, these 2 are out, this one is out. Okay, then you look at things like iron 3+, right? So this is the worst. This has 5 spin polarized electrons, so this is largely ambivalent about its coordination. Iron 3 can do tetrahedral, iron 3 could do octahedral. So this is a terrible ion to work with in a battery because it moves all over the place. Okay, so iron 3 is out, and therefore iron 4 is out as well. What about manganese 3? You sort of think maybe that would be okay. The problem you have with manganese 3 that it disproportionates. It makes manganese 2 and manganese 4 sometimes, and manganese 2 is terrible, right? 5 electrons, it's a half-filled D shell. This thing moves all over the place because basically it's ambivalent about its coordination. So those are out, but the one you can use is manganese 4. This is perfect. 3 electrons, if you don't oxidize it, you stabilize octahedral coordination. And now you see where our battery chemistry ends up from, right? We use manganese 4, we use cobalt 3. This is the perfect ion. You have 6 electrons, non-spin polarized. You have 6 electrons that fully favor octahedral coordination. And indeed, the one element that we never ever see move around is cobalt-3. And it's sort of ironic, that was the first cathode ever invented, probably by accident. Maybe John Goodenough knew all this, but I don't know. But it turns out to be also, I'm sure he did, thank you. Is in some sense by far the best elements. But this is the problem, right? So this is not something you fix, right? This isn't something you engineer away. This is basic physics that kills your mobility ultimately. Okay. So how do you break this curse, right? Because we cannot keep on more using cobalt. By 2025, we will use 25% of the nickel market for lithium-ion batteries. This is an enormous number, right? Because nickel is mainly used for stainless steel. So the nickel market is about 2 million tons. And you know, that's a very large market, but we're going to use 25% of that. And by the way, we cannot use most of the nickel coming out of the ground is ferrous nickel alloy, which gets dumped straight in stainless steel, so it cannot go to the battery industry, right? So there's going to be an enormous demand on nickel, so we have to go away from this, right? So let's go back to basic science, how you fix that problem. And the one is to think back about what really caused the problem. What caused the problem was the transition state, right? We had this transition state, which is the tetrahedral side. Lithium has to go through there. Usually there's one vacancy here. In most cases, there's actually two vacancies. Lithium tends to diffuse by a die-vacancy mechanism. But you're close to this transition metal. What if you could change the transition state, right? If you just look at the different possible populations around the transition state, you could have more transition metal, but you could also have less. If you have enough lithium around, in principle, maybe you could make transition states with only lithium around them. And now you're in a better situation, right? Because when lithium diffuses in here, remember this one and this one would be vacant, it now only sees another 1+ ion. So now you have a 1+ ion seeing another 1+ ion, so your electrostatics is going to be much less. So hopefully you will be much more tolerant to contraction of this tetrahedron, right? And that turns out if you do ab initio theory, that's what you find. We artificially set up configurations with a lot of this 4 lithiums or 0 transition metal, as we call them. And again, this is now the size of the tetrahedron. If you reduce it, the activation energy goes up only by a little. Whereas if you have 1 transition metal there, it actually goes up a lot more. So the key for us to be able to work with condensed systems that are much less sensitive to lattice parameter change, is to create mobility through these what we now call 0TM channels. And so how do you do that? Well, if you have ordered structures, in these layered structures, there are only 2 environments, this one and this one. And this one is the one you use. But if you were to disorder the material, if you were to start randomizing the cations, then you would statistically create all kinds of environment, right? And if you can make enough of these, you can actually get diffusion. So what we thought of is like, can you make disordered rocksalts? So they're still crystalline materials, but the cations are now disordered, so that statistically I get some of these, and then can I make enough of them that they percolate? Because I need diffusion throughout the whole crystal, so I need what's called percolation of these environments. And it turns out that you can percolate if you put about 10% lithium excess in. And that was kind of the breakthrough that one of my brilliant students, Jin Yuk Lee, did with Alex Urban. Alex Urban was the theorist. This was one of these great moments in your career where the science was all done in 2 weeks. There was sort of an interesting observation in the lab. Everybody got very excited. And for 2 weeks, we sat almost every afternoon and every evening together and worked it all in 2 weeks. And this is when you sort of wish that you could do that every time, and then you realize that only happens every 10 years, right? Those kind of moments. But then you live on them for 10 years, right? So this paper came out in 2014, and since then we now have $1 million research programs, and we're sort of milking it for all it's worth. This is the design map, essentially, that this is the lithium excess. This is the cation mixing. So here you are ordered, here you are disordered. That essentially when you cross this line, this is the percolation line, you can actually operate with cation disorder, right? And again, you see now why that's important. We can operate with cation disorder. That means we can use any chemistry in the periodic table because we don't care if the ions start to migrate out of their ordered configuration. So the first material in which we did that was actually a material that started layered. This is a lithium molychromium oxide. This is a STEM picture. And you actually see the layering, right? Where you don't see anything, that's lithium because it has low Z, right? So this is a well-layered material. This is after 1 charge-discharge cycle. So contrast starts to show up in the lithium layer. This is 10 cycles. this is a fully disordered rock salt. But the remarkable thing is after 10 cycles, that's sort of the green line here, we still have full capacity in this material. So this was sort of the first proof of concept that you could actually make a disordered rock salt that had really good lithium transport and lithium percolation. Since then, like lots of people have appeared on the scene, made all kinds of materials with very different chemistries, and you know, if you look at this, this has a lot of chemistry that is not present in today's lithium-ion materials. We use molybdenum, chromium, vanadium, we use niobium, we use titanium. So in some sense, we've really kind of unlocked the periodic table here by doing this. We've been able to go to really high energy contents, almost approaching 1,000 watt-hours per kilogram, which in contrast today, best cathodes are about 650 to 700 watt-hours per kilogram. And we can do it with fairly cheap elements like manganese and titanium, right? This one is manganese and niobium is not the greatest. It's in a similar situation like cobalt, but this one is actually very good. Okay, let me sort of skip that. So we've unlocked the periodic table. Okay, so I think that the resource problem in lithium-ion is going to be there for the next 5 to 10 years because it takes a really long time for new materials to commercialize. And the next 5 or 10 years we're probably going to do with existing materials. But after that, things may clear up. So what I want to talk a bit about is also where can we go beyond lithium-ion, right? What comes after lithium-ion, if anything? And my feeling is that there's going to be a diversification of technologies based on what you prioritize, whether you prioritize low cost or high energy density or safety or so. And so on the lower cost in principle, you can do the same with other alkalis, right? What you do with lithium, you can in principle do with sodium or potassium. They intercalate into crystal structures. The salts of sodium and potassium are a lot cheaper. The cathodes tend to be cheaper for reasons I don't really want to go into. A lot of them function with metals like manganese, and so if you go for specific energy, so this is energy by weight, things like lithium sulfur and maybe lithium air look somewhat interesting, although these have been on the table for a long time and have been challenging. I'm mainly going to talk about what you want to do if you go to high energy density or high safety, and that's just because I don't have time to go through all the other ones. The one many years ago where we thought we should go for high energy density is using magnesium-ion, and I'll say something about that in the end, because now you're moving a divalent ion instead of a monovalent ion, so you can in principle transport twice the charge, right? But the one I really want to talk a little more about is solid state lithium, which probably will get both high energy density and high safety. And you know, I don't totally know where to put flow batteries, which has been sort of on the map for a long time. And flow is really interesting for grid, but my worry is that as some of these get better and cheaper, that flow gets kind of crowded out by these cheaper technologies. Okay, so let me get a bit into solid state. The primary driver for solid state is safety. And the reason is what makes a lithium battery flammable is not the lithium, it's the organic electrolyte. So we use an organic electrolyte, it's a carbonate solvent, which has a very low flash point. And so the typical incident is in the battery is either one of two. Cells get punctured in an accident, electrolyte leaks out, you're in a high voltage environment, you have sparks and things blow up on you. Or the other one is you have an internal short. And internal short, the battery releases its energy very rapidly. The cathode is highly oxidized. It oxidizes the electrolyte, right? Because the electrolyte is an organic solvent, and you have an explosion sort of internally or fire internally. The last one was essentially the incident of the Note 7 incident. But there have been other ones, right? Shittily based batteries in hoverboards. Like I said, the Boeing 787 incident, which grounded the whole fleet. So the way to solve that is to replace the material with an inorganic solid. If you replace the conductor with inorganic solid, then in principle, it's harder to oxidize that, so you don't really have a fuel anymore. And that was thought to be really hard because people always think that you can't really make very good conductors, not as good as liquids, but I'll show you that that's possible. The other reason to do this is that we think that there's sort of a trajectory to bring lithium-ion from about 600 watt-hours per liter, where it is today, to probably about double, 1,200 to 1,400 watt-hours per liter, if we can use lithium metal anodes. Okay, so what might enable this? Well, in 2011, there was an interesting paper in Nature Materials by Kayama and et al. who showed a new conductor, lithium germanium thiophosphate, LGPS as it's called now, which on an Arrhenius plot has the same conductivity at room temperature as liquid electrolytes. Interestingly, it actually has a lower activation energy than liquid electrolytes, meaning at low temperatures it's actually even better than the liquid electrolytes. Now, they claimed very high conductivity, 12 millisiemens per centimeter, which is exactly kind of where organic solvents sit. They claimed it was a one-dimensional conductor, has a super high electrochemical window of stability over 5 volt. The interesting thing about this paper is that it's almost completely wrong, except for the important thing, the conductivity. So almost everything in this paper has been proven wrong, but fortunately, the material indeed has super high conductivity, and it's sort of remarkable, right? It's a material with, I mean, this is a remarkably low activation energy for motion of ions through a solid. We jumped on that right away and did ab initio simulations. This is just a pretty picture where we sort of show that indeed you have very high conductivity. But we showed, first of all, and this has been confirmed by others, that it's not a one-dimensional conductor, that it's a three-dimensional conductor, because you have diffusivity in all 3 directions. And that makes sense. One-dimensional conductors are terrible because they have channel blockage. So even fast one-dimensional conductors tend to not operate in a macroscopic mode, because anytime you put a defect in the channel is completely blocked. Whereas in a 2-dimensional conductor, you need a large amount of defects because you have a single defect, you can go around it. But in a channel, you can't. So one-dimensional conductors rarely are good for high ionic conductors. But there are other things about this, right? So first of all, this uses germanium. Germanium is a non-starter for the battery industry, right? As my friends at Umicore said, you know what the world production of germanium is? It's about 20 tons, or the way my friend puts it, that's 2 trucks here. 2 trucks of germanium is the world production, right? And by the way, there are other people who will pay a lot more money for it. People who do infrared detectors, silicon germanium wafers, they will pay a lot more for it than battery people can actually pay for. So the question is, can you make other versions of this material? You know, to us, this was a proof of concept, so we right away started figuring out, well, can we replace sulfur? Sulfur is not great, right? If you expose sulfides to air, they make H2S, which is not a pleasant thing to work with, right? People are really worried about that in factories, because you can all control it until something goes wrong. You get moisture infiltration in your process, and suddenly you have to evacuate the factory because you have toxic gases going around. This is actually not so much a problem in the battery. This is really a production problem. So we wanted to see, could you replace it by selenium? Not that selenium is better, but if you could replace it by oxygen, that'd be awesome. And germanium is a non-starter because of price, right? And could you replace it by things in the same column, silicon or tin? So this is a great ab initio problem, because you can first of all look at the stability of these compounds. So what we do is we calculate essentially the substitutions with silicon and tin, and then on the anion with oxygen and selenium. And we calculate the energy by which it's stable or metastable. And this is actually the energy by which it's metastable. And this is actually the compound that's been made. So the sulfur germanium version is metastable by about 15 millielectron volt per atom. But what you see is if you go to tin or silicon, that doesn't really change dramatically. Or if you change sulfur by selenium, that doesn't change much. So in principle, these should be able to be made. You can calculate, they have similar conductivity. The silicon one is actually slightly better even. And indeed, a few years later, so the prediction was in 2012, in 2013, 2014, people made the tin version and the silicon version, and in 2015 the tin version became commercial. You can actually now buy it from NEI, and this is actually now the conductor you'll use instead of LGPS, the germanium version. So a fairly fast pace here from kind of novel conductor synthesis and verification, but that was in part because these were largely substitutions on known compounds, right? We didn't come up with a completely new crystal structure or so. Okay, so that made us think a bit like, is there more, like, right, what makes a really good conductor? And so we started thinking about it, because now that there was this proof of concept, maybe there are even better conductors, and maybe we should forget this paradigm that liquids, because everything's kind of loosey-goosey, that it's a better conductor, right? So you start sort of thinking, okay, a bad conductor is if you have very high energy landscapes, right? If this ion has to go over a very high barrier, then that's not be a good conductor. So the question is, how do you flatten barriers in solids in general, right? Okay, so this would be a good conductor, right? Well, one way you do is, what you want to do as this ion moves, right, you want to minimize the change of interaction with the other, the rest of the structure. Because it's all about how flat the energy landscape is. So if you never change the interaction or have low interaction in general, then you can make a good conductor. So the first thing you do is you want to screen the interaction with the other cations, right? Because there are other cations around, they give you electrostatics. So in general, a sulfide will be better than an oxide. Sulfur is a big whopping anion with fluffy electrons, as I like to say. So they're amazing at screening, right? Sulfides will be better at screening than oxides, and selenides will be even better. But there's another issue that's often forgotten. You know, the diffusing ion, like lithium, also gets a lot of its energy from the coordination by the anion, right? So as it changes its coordination, it's really changing its electrostatic energy from the anion environment. So you really want to minimize coordination change as you diffuse. And that was a key insight, because we started looking at different packings of anions, and something that you probably teach in like freshman material science became suddenly very important, that if you look at BCC versus FCC, they have very different interstitial voids counting. So if you have BCC, you have a lot of tetrahedral voids with phase share with each other. Whereas if you go to FCC, remember lithium prefers mostly tetrahedral sites. If you're in a tetrahedral site, the only way to get to another tetrahedral site is to go through an octahedral site. So based on what I just told you, what's going to be the better conductor, right? The better conductor is going to be BCC, because here you only go from 4 coordination to 3 as you go through the phase, 4. Here you go 4, 3, 6. This is terrible, right? And indeed, if you actually calculate the raw diffusion barrier, if you know, in computers we can do amazing experiments, right? We can literally take an S2 minus lattice without any other cations, right? And we look at, if you do it in a BCC one, your activation energy is only about 0.15 eV. If you could realize that, you would have a conductor at the order of hundreds of millisiemens. If you do FCC, you get like 400 MeV, right? So this is a pure anion effect. There's nothing else around. And indeed, if you look at some really good conductors like LPS and LGPS, they have BCC anion backbones. If you just take everything else away, the anions show a BCC structure. Whereas if you look at some worse conductors, they have HEP or FCC backbones. So this was a key insight, because now you go like, I'm just going to look for more compounds with BCC backbones, right? And so you search through the ICSD, you code up a few algorithms to look for how the anions are packed. And we found one that actually nobody ever thought about, is a lithium zinc thiophosphate, or LZPS as we call it. It has a BCC backbone. By itself, it's not a good conductor. You have to put in carrier, so you have to lithium dope it. And we predicted that depending on the amount of lithium doping, we could get as high as 100 millisiemens. So remember, that's a factor of 10 above the best known solid-state lithium-ion conductor there. But as always, nature is against you, right? And so it turns out if you calculate the phase diagram, this is LZPS, this is a solubility limit, this is the lithium content. Our target composition, the optimal composition, is right in the 2-phase region, right? So if anything, we would have to make a really metastable compound that sits in the 2-phase region. So we have never been able to actually get to that composition. We have been able to get reasonably close over many years by working with our collaborators at Samsung by improving processing methods. And we are essentially now within an order of magnitude of the target. That may seem like terrible, but in the world of ionic conductors, an order of magnitude is not a lot in terms of milli-electron volts. So by now, it is among the best conductors, but it is not as nearly as good yet as we predicted. Okay. So I think we start to know fairly well how to make good conductors. And I think what we're learning is that there are probably many more good conductors for ions than we actually thought there were. That this is actually not as unusual as we thought. But if you're going to make solid-state batteries, there are many other problems to solve that I don't have time to talk about. I want to introduce to you, if you want to get into a hot field, because this is going to be a hot field, no pun intended, that there are several other problems to be solved. There's electrochemical stability, right? So you're going to take a sulfide and you're going to put it between a cathode where you're super oxidizing and an anode where you're super reducing. Lithium is like one of the most potent reducers, right? It reduces everything it sees, right? And you know, with a sulfide, there's going to be a problem. Sulfur gets oxidized at 2.5 volt, and I want a 5 volt battery, right? I want a 4.5 volt battery. But the biggest one is mechanical issues. So cathode materials swell and contract as they take up lithium. If you do this in a liquid electrolyte, the liquid just displaces and comes back. Now I'm going to have to make microstructures that are completely solid. Right? These are composite microstructures. They actually look like this. Let's say the blue thing is the active cathode, and then in between sits the conductor. But now you have to think of this as sort of a sintered or pressed composite, right? That's how this is going to look. And so this cathode is going to swell, contract, and you want to do this 1,000 times, right? You need 1,000 cycles. So the question is, how do you keep contact, interfacial contact between these conductors and the cathode? So this is a major issue. The other one is, to make this worth our while, we also want to go to a lithium metal anode, right? Today we use graphite, but if we can go to lithium metal, we don't use lithium metal today in liquid ion batteries for safety, because lithium tends to easily form dendrites when it's plated, and it sort of just makes a dendrite, and it short circuits to the other electrode. People have this belief that in solids, because solids are hard, lithium is a really soft metal. The yield strength of lithium is like 0.7 megapascal. It's a little above butter, right? And so people believe that if you put a hard solid in between the electrodes, lithium will not get through it, and so you won't have shorting. Well, that's what we thought. Here's a result from Sakamoto's group in Michigan, where this is actually an oxide conductor, but it's a polycrystalline. And after a bunch of cycles, lithium has completely grown through the grain boundaries. So this is actually lithium you see everywhere. It's literally like, it's almost like it's etching the grains, right? It's a beautiful picture. So okay, you think it's only grain boundaries, so I'm going to make something without grain boundaries, and maybe you make some kind of amorphous film, or hell, a single crystal. Well, this turns out there's some work now that's shown that lithium fractures a single crystal. And we don't know how that happens. We do not understand the chemomechanics of how a metal that's 0.7 megapascal fractures something with a critical fracture constant that's like hundreds of times bigger, right? And you know, when you don't understand things, people come up with amazingly esoteric theories that maybe lithium gets a lot stronger when it's confined. And you know, there are people who've claimed that the yield strength of lithium in confinement is 200 megapascal. And I go like, well, I've never seen that kind of confinement effect, right? Going from 0.7 to 200. But this is sort of a real kind of, this is one of these real puzzles in the battery field today. Like, if we don't solve it, we will not use lithium metal, because we have to be able to deal with the mechanics issue of lithium. Okay, so finally, the last thing, and then I'll close, is, you know, can you go to magnesium-ion batteries? And magnesium is really interesting. It's very cheap. It's quite safe, because if you expose magnesium to air or water, it instantly passivates. And that helps you against runaway reactions, right? If magnesium gets exposed to anything, it makes MgO, or magnesium hydroxide. And magnesium oxide must be one of the most impenetrable oxides there is, right? A good cocktail party story is that, you know, the density of magnesium ions in magnesium oxide is higher than in magnesium metal, right? It's because it's such a densely bonded material that you can get, there's almost no point defects, you can get nothing through. So the magnesium anode is extremely passivated. But it has enormous charge density, right? So if I take an equivalent lithium anode and I now take the magnesium equivalent in terms of the amount of charge, you see it gets super thin. So in principle, in terms of energy by volume, which is, by the way, the criteria that most applications care about, not energy by weight, magnesium anodes would be enormous. So what's the challenge? There are essentially two challenges, right? You need cathodes with very high magnesium 2+ mobility. And that's hard, right? You now have a divalent ion that polarizes its environment a lot, so it's going to be much harder to move. And you need electrolytes that can run magnesium without passivating magnesium metal. Because if we passivate magnesium metal, the game's over. Magnesium oxide is impenetrable. So proof of concept was done already back in 2000 by Doron Auerbach in Israel, who showed a working magnesium battery with a Chevreul sulfide cathode. And this is remarkable. This runs at room temperature, but the voltage is low, the capacity is low, but it is a proof of concept. The problem is that since 2000, we haven't exactly made a lot of progress. We made a little bit of progress, again, by thinking logically about the diffusion. And this is the story on which I'll end, is that the answer for making a good magnesium diffuser turned out to be remarkably simple. Again, if you think of this landscape, right, you want to get this down and this up. So if you want to move magnesium, you want this site, the stable site, to be one where it sort of has unfavorable coordination, and you want to be the activated state to be one where it has more favorable coordination. And if you look at sort of the typical coordination environments for magnesium, they are mostly 6-fold. Magnesium is usually preferred as 6-fold, and occasionally goes 4-fold. So what do you want to make? You want to make a material where this is 4-fold and this is higher, like 6-fold. Duh, like, you know, so some old style ceramist among you, that's a spinel, right? That's a spinel, right? Because in spinel, you push you push one of the ions tetrahedral, even sometimes when it kind of prefers to be octahedral, and then because the spinel is an FCC oxygen packing, to diffuse from one octahedral site to the other, from one tetrahedral site to the other one, you have to go through the octahedral site. So this is perfect for magnesium, because magnesium prefers octahedral, but in spinel it's pushed to tetrahedral. So it's going to sit in a slightly unhappy site, and then as it diffuses through, it becomes happier. So you get a chance to bring down the activated state. Okay, so if you calculate that, if you do that with an oxide, this is the migration path. It's still pretty high. It's about 800, 850 MeV, which is still too high to do at room temperature. But if you not get a little help from your friends, the anions, and you go to a sulfide spinel, because of screening, you can bring this down to 600 MeV, which is not quite like lithium-ion, but that actually works. So this is a work we did with Linda Nazar as part of J. Caesar. If you take a titanium sulfide spinel, which you make by making a copper titanium sulfide one and leaching out the copper, you can actually cycle this at very high capacity. This is comparable capacity to lithium-ion, 200 milliamperes per gram. And we're higher up in voltage than we were with our Auerbach's paper. We're sort of at the 1.25, 1.3 volt, but we're no means competitive with lithium-ion yet, right? Lithium-ion runs at 4.5 volt. But again, a sort of proof of concept that if you start thinking about how things should diffuse, you can make better materials. So let me kind of end with this, right? I think a lot of this I've already said. You know, energy storage is a big deal. I didn't realize that when I got into it, but it's sort of an amazingly growing field because it touches so much of what we do, right? Whether it's portables, whether it's renewables, whether it's transportation. The lithium-ion market has just had stupendous growth, right? I think resource constraints are something to think about, and they will definitely plague us in the short term, right? The industry is ramping up tremendously, and it's ramping up with the materials we know today, not with the materials we're making in the lab. In terms of new technologies, I would say most effort in industry and in academia is really moving to solid-state lithium-ion. And I think because while it may not be amazingly better when it comes out, people see it as a new development curve. Lithium-ion is obviously plateauing in terms of performance, not in terms of cost. But solid-state, people really see solid-state is going to move you onto a curve where you probably will double energy density in the long term. So my worry from an academic perspective, if solid-state hits 1,000 watt-hours per liter, the game's kind of over. All these other things that I put on the board, right, is going to be extremely hard to compete with them. And I think that leads me to sort of some thoughts that I've had, both as an academic and trying to make a business out of this, is I don't want to quench people's enthusiasm, but when you bet against incumbent technology, think hard, right? Because when you're trying to do something new, you have to compare yourself to what that incumbent is going to be 5 years out, as I said, right, or 10 years out. You know, when I was a graduate student, I got courses in microelectronics materials, and everybody said silicon was dead. It was all going to be gallium arsenide, right? That's like 25 years ago. What is today, right? It's all goddamn silicon still, right? And we've seen this time and time again in technology that, you know, in industry, incrementalism is not a bad word, right? It's only in academics that it's a word. When they improve things by 5% each year, that adds up to an enormous amount. And again, that doesn't mean you shouldn't try to do new things, but think about where your competitors are going to be in the long term. And I've been so long in the field now that I remember either hearing these quotes or making them, sadly enough. And they were all wrong.
They were all wrong. People would say the cost of lithium-ion is too high. Today, it is almost the cheapest form of energy storage you can buy, right? It's come down to like $100. Oh, lithium-ion is never going to be in the grid. Like I said, like over 95% of energy storage in the grid that is being put in today is lithium-ion, right? Lithium-ion cannot do fast charge. That was one until like, 10 years ago. People say, lithium-ion is slow. You need nickel metal hydride for fast charge. You can make cells if you wanted to that charge in 2 minutes. Right? It's all engineering. It can all be done. The material science is there. It's actually been done in the lab. The biggest problem for Tesla to make their car charge fast is not the battery, it's the power supply, right? Do the math, right? If you have an 80 kilowatt hour battery and you want to charge it in 5 minutes, right? That's 1,000 that's a 1 megawatt power rate, right? Where can you get the 1 megawatt power rate, right? And it's simple things like ohmic heating of the cables. It's actually not really the battery chemistry anymore. So all three of here were sort of wrong, right? And the last one, which I kind of like to use in my that whether you do applications or not, I think that trying to understand what's going on goes a long way. The reason we could invent these disordered rock salts, which was in 2014, is because I had a brilliant student in the mid-90s, Anton van der Ven, who's a student now at Santa Barbara, who spent his whole thesis trying to understand how lithium diffuses in solids, right? And at that time, we had no idea that we were going to make new cathodes out of that. But because we understood the principle of the dye vacancy mechanism, things moving to the tetrahedral site, like that sort of 15 years later, that suddenly became like truly useful. And so, whereas if you make things by accident, that's great. But if you understand them, understanding is kind of forever, right? That's the way I sort of feel about it. So with that, I'll end with my philosophy statement. So thank you.
Yeah, I had a question on some of your issues that you raised and the challenges, and the ones on the mechanical issues when you said obviously the cyclic expansion and then in the discharge you get contraction. What's the magnitude of the cyclic strains you talk about there in those kind of conditions that's going to last 1,000 cycles?
Yeah. So typical volume expansion of a cathode. So the cathode are typically 5 micron to 20 micron agglomerates of particles, and they would anywhere between 5 and 10% volume expansion. They would expand. But then remember, the actual cathode film is a composite. You put a lot of these particles in a composite together, and that whole thing is about 100 micron thick. But yeah, sort of 5 to 10% is a typical number. We are asking ourselves sort of the question where you can make cathodes that have zero volume expansion, which is an interesting scientific challenge. It's not impossible, but it's always like you have to satisfy a lot of engineering constraints, right? So I can make a cathode with zero volume exchange, but then you won't like it for other things. And that's sort of engineering always for you, right? It's never about one property. It's about like getting 5 or 10 satisfied together and trading them off. But it's a major issue. It's also, by the way, an issue on the lithium side. If you're going to make a solid-state battery with lithium metal, you're essentially just plating and stripping that lithium so that interface with the solid-state conductor moves back and forth, right? So the only way we can run a solid-state cell today in the lab is by putting very high stack pressure on it. So we run it at like 4 megapascal stack pressure, and then it is okay, but that is not a commercial viable solution. There's no way you can make a cell that's going to put 4 megapascal pressure on.
I got 2 quick points.
Well, so I like your quote at the end about fundamental understanding, and you get nice talk about. I find it interesting how you think of all these structures as rocksalt based. But in the beginning, you also said they are layered, right? And the way I think of lithium cobalt oxide is the cobalt 2 is negative, the lithium is positive. Lithium gives its electrons, so the cobalt 2 is happy. But now you take the lithium away, and the cobalt 2 isn't happy anymore because it becomes metallic layer because p-type dopants. Because it misses its
You've rolled over the cobalt oxide layer,
right?
Yeah.
So how much of the lithium can you take out without making the cobalt 2 unhappy? So
more than we thought. So the idea is sort of like, when you start taking lithium out, you're doing 2 things, right? Obviously, you're creating a lot of vacant space, but then you're changing the valence state of the cobalt. You can think of it as p-doping. And obviously, these materials become highly metastable, right? But you're operating at room temperature in principle. That the fact that they're metastable is not a given that they will fall apart. We used to always think they would fall apart, but what we're actually finding is that these structures remain remarkably metastable, and you can, it's not clear that structural stability on things like lithium cobalt oxide is the limitation to their operation. That is not always true for some other ones, right? Again, whether you go from your metastable state to your stable one depends a bit on mobility of species. And the mobility of cobalt is so bad because of this octahedral stabilization that it just has nowhere to go. But if you do this with, say, some pure manganese-based compounds, you will see structural instability. The biggest problem is actually that the compound is highly oxidized, right? You make cobalt-4, which is a highly oxidized state for cobalt, and that this thing basically oxidizes everything in sight. So it's more of an interfacial problem that where the cathode sees the electrolyte or the binder or the carbon, it just wants to give off oxygen. But that's because it's a material that's already inherently stable. When we work on new materials, we often see the problem of structural instability. But once you've solved that, you still have problems.
So I was interested in some other layer oxides like MO3 and V2O5 where the metal transition is its highest oxidation state. So when the layer structure, the oxide is stable by itself, you can still put lithium or sodium or even magnesium in between them. Yeah. And then, why isn't that a better route? So I know that people have tried V2O5 for batteries, but I don't know why it's never made it.
There's some technical reasons. One is that if you work with first of all, if you work with a lithium-ion battery, the anode is graphite, so you need to bring in lithium somehow. So V2O5 doesn't come with lithium, so you have no lithium to start with. But the main one is that actually V2O5 has the opposite problem, that if you put a lot of lithium in, it starts transforming to other structures. So it's stable in the charged state, the one without lithium, but it's not quite stable when you put a lot of lithium in. And the other one is that the industry doesn't like vanadium, right? Vanadium is sort of in that sort of semi-toxic category, which I coined myself. Semi-toxic sort of means that toxicity is not terribly bad, but it's classified as toxic, which means that you have an enormous administrative issue when you deal with it in plants. But the main issue is that fully lithiated state is not particularly stable for V2O5.
So I'm curious about this percolation threshold with the lithium. It seems to me to percolate at 10%, you have to have some ordering force. You wouldn't get random population wouldn't be. What is it that causes that percolation threshold to be so low?
Oh, so it's actually 10% lithium excess. So that means in the stoichiometry, it's 1.1 lithium, 0.9 metal. So it's actually 55%. Sorry, I didn't say it. But you bring up a good point. More and more what we're learning is that even when things look like disordered rock salt, they have a substantial amount of short-range order in them. And that changes the percolation threshold. And that's why we're learning now that we need to characterize the short-range order carefully to get a better assessment of percolation.
Is it electrostatics mostly, or strain, or both?
It's the balance between the two. So you point at it exactly. You can understand the short-range order largely by the balance of the electrostatics and the size issue, which is something we have sort of just made it work through, I would say.
If you really wanted to bid against incumbent technology, I'm wondering what you've been discussing is to take the God-given crystals that we can have and transporting ions in them. Is it conceivable to use self-organized nanostructures for such transport, which would give you a greater flexibility in the engineering things?
I mean, yes, absolutely. So one issue you have to keep in mind that, so in batteries, the issue is largely about energy density, right? So you cannot give up volume. So while porous things look kind of appealing from transport perspective, from an energy density perspective, they're terrible, right? And the reason energy density is important, it's not just because my phone likes to be small, it's also because it drives cost. So if you have low density cathodes, you only get a certain amount of energy in a cell, and then you need to make more cells, and that kills you, right? So we've done this analysis at one point. Even if I take a material with, say, half the energy density of what I have today, but I give it to you for free, right? It doesn't cost any money, I still lose. Because I just have to make a lot of batteries, I have to wire them together, I have to do things like that. So it can definitely be done, but you have to always keep density in mind. And these oxides, these have very high density. Lithium cobalt oxide is 5 grams per cc. So for a 3D metal oxide, it's actually very high, which is why it's so popular with Apple. Whatever the cost, Apple and Samsung will never give up lithium cobalt oxide, whatever they say. Cobalt today is probably $60 a kilogram. It can go to 500 and they will still not give it up. So I think where self-organized structures may become really important is in solid-state batteries, right? If you can make these intergrowths of, say, the conductor and the cathode, right, in some self-organized way, you can do much better than we do today. Because today what we do is we mix them together and we press them or we sinter them, right? It's pretty primitive in that sense, right? It's kind of not exactly organized. It's pretty random. And so if you can do that in a more controlled way, like with some kind of assembly, you could probably do much better. But again, you have to do it cheap and fast, right? So today we make lithium battery sheets, right, at about 1 meter a second coating. Right, so this is a big sheet like this, right? It runs through a coater, slurry coating, runs through an oven, and then it gets slid up in pieces that you wind up in a cell. So you have to, in the end, be able to compete and do it at seriously high processing speed, right? Because I can make solid-state batteries with semiconductor processing technology, right? Easily, but that's not going to cut it, right?
You showed an interesting image of that lithium penetration along the grain boundaries in that one system. Does that depend on the kinds of boundaries? At least the image that you showed looked long enough that all the boundaries were coated. But earlier in the stages, do you get different amounts of penetration depending on
we don't
that?
know. This is actually kind of very early work, and even this is occasionally disputed. So there are people who claim that this doesn't happen, but I think sometimes that's wishful thinking. There's been so few studies about this that it's really hard to say.
Because we talked to work a long time ago on solid metal embrittlement, where solid metal penetrates certain materials and embrittles, and this kind of has that.
And people have started thinking like the stuff people know from ceramics processing, can you do like oriented grains where at least you can make the path longer? If you had long flat grains, right, and the lithium has to come this way, you'd have to kind of change the orientation. And whenever lithium goes parallel to the electrode, there's actually no electrical driving force for it to continue to grow. But the battery field is not very sophisticated when it comes to ceramics processing, right? Because we basically didn't need any until recently. And I think, as I was saying over lunch earlier, one of the problems with the battery field is that because it's an applied field, it often takes 5 years for it to get the skills it needs whenever it changes direction. And solid state is one of those, right, where basically we need a lot of mechanics, we need a lot of ceramics processing, which basically we don't have today, because it was all about solid state diffusion, it was about electrolytes, so in some sense the winners actually that you see emerging are people who come from outside of the field today in solid state.
Are there any lithium analogs of beta alumina, these spinel blocks?
Well, as you know, lithium is a terrible conductor in beta alumina, right? Because it's not sort of size mismatch. So I don't know of any that look like that today.
There should be.
Yeah. But the nice thing about sodium, it's a big ion, right? And in some sense, a bigger ion is almost easier to transport because you kind of smooth out the corrugation of the energy landscape a bit. I mean, I know it's a bit simplistic language I'm giving, but we find that it's actually easier to make good cathodes for sodium with high mobility than is cathodes for lithium. And potassium, potassium is a rock star. I can diffuse potassium through anything, basically. Because it's so big that it just kind of, like if you do potassium in a layered compound, it just props open the layers and it goes like straight through. Whereas lithium is the one that gets kind of like trapped in the pockets, right? And that's why magnesium is terrible, right? Because magnesium is the same size as lithium, but it's not double the charge, right? It's the worst ion ever, right? So we're actually thinking that magnesium batteries is probably not the future. If you're going to do divalent, you probably want to go calcium, right? But now you're talking calcium electrochemistry. Now, here's a challenge for an electrochemist. We don't even know how to make a calcium metal anode work in liquid electrolytes, right?
Okay, well, we have yet some more formalities to undergo, so let us thank Professor Sager.
Give you this plaque.
Thank
which
you.
says the Case School of Engineering, Department of Material Science and Engineering at Case Western Reserve University honors Gerbrand Cedar as its Van Horn Distinguished Lecturer for 2019.